Alrighty. Okay, people, welcome back. We're going to talk a lot more about scaling today. I've added a few more slides to the set that I was moving through last Thursday, so I've expanded a few pieces that I've been meaning to add for a while. So we're going to see some strange things, all right? Some strange kinds of scaling, all sorts of examples. We'll get to that. And then we start on parallel size distributions, right? So this is statistics of surprise, right? You sample, 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 nothing happens, and then you get a major earthquake. That sort of thing, right? So that's a really fundamental kind of feature that goes across lots of different systems where things can go boom. And we care about that, right? Because boom is not good. Okay, unless you're a bad guy. All right, so you're good guys. All right, I'm away next Tuesday, so let me write that down. So there won't be an in-class thing. I'll make something up with the magic thing, okay? Next Tuesday, which coincides with some IGERT vanishings as well, right? Okay. I'll be in Napa. Conferences, interesting. Okay. I try not to go to them. They just waste my time. Okay, so that should be good. Future of computing or something. Okay, there's that. Assignment 1, still due. Okay, that is still due. That's Friday, 11:59 p.m. for no really good reason, but it gives you breathing room. So you should specify your own finish time for that.
It does say to go back or before class time on Thursday, like if you go onto the.
It's still run? Yeah.
So I just want to make sure.
Okay, I'll fix that up. It should be on the actual assignment. Let me see that. I've made things too sneaky sometimes. Assignment. When does this actually say due? Does it say due? This one doesn't have it, I guess. Is that true? No. By start of lecture, you're right. I gotta fix that. I gotta fix that. Okay. The website usually should be the healthiest place. And that one says, yeah. Okay, I'll fix that up. Thank you. Assignment 1, due date. It's not a good abbreviation. Okay, so good. Thank you. Yes?
For undergrads, for the assignment, can you handwrite it and then just say it's
Yeah, that's the idea. So just handwrite it, scan it. Scannable being the recommendation. I get no money from that, but like I'm just saying. I think that's a good one. They're kind of magic little things, right? So that would be good. So, and if you can do that, make it as a PDF, right? I mean, in the past, I've gotten 23 JPEGs, and then I have to write a little script that sticks them all together and sends them to the grade. So which I will do because that fits my nature, but it's not efficient. Yeah. So one solo PDF, that would be great. Good. Just shout questions. It's okay. I get carried away with what I'm doing. So let's see. So that's most of the stuff. So I'm going to talk about scaling. Okay, good. Was there anything else? Okay. That's it. I know there's some audio glitches, unfortunately, in some of the recordings. I'm trying to do new things. I'll fix that. Again, insanity, but I'll fix it up. Okay. But do tell me, just let me know by email or whatever. I will try to fix all these things up. Okay, so we were into this, we were talking about biological stuff, and I think we ended with this example of scaling in cancer probability, right? Which is a sort of profound and kind of shocking thing. So I've interspersed a few more slides back in here. So let's go back, and I'll sort of skip the ones we've already talked about. So we had this one about weightlifting. Scaling is a 2/3 power. There's a couple of sort of human performance type things, including, even Moore's law is a human performance type thing, right? So people getting better at something. So this is from world records for running and swimming. So these are running and swimming, and it's a bit odd, but these are the times for a series of events, right? So it'll be the 100. Is that true? Yeah. I guess this is it looks like 10. This is 10. It's meters per second. So this is speed as a function of how long it took. Fine. So this should be the 100, the 200, 400, 800, and then we'll get into 1500, the mile, and then should be 5K, 10K, half marathon, and so on, right? And what you notice in all of these scalings is this clear break, and it's around about So I have the numbers here. So it looks like we have this kind of the speed, the average speed of the very best times is scaling like tau to the minus beta. So tau that it takes, tau's the time it takes. Again, there's not a lot of range on these scales, of course, that's the way it is. It's pretty weak, so that we're going to say this, small scaling regimes. This is a paper in Nature in 2000 by a couple of astrophysicists, so that's what happens. About 100, so 2.5 minutes to just under 3 minutes. There's a break in the way scaling works, right? So there's this is a steep drop in the speed, and then it still drops, but at a slower rate, right? And there are estimates that people have, if you can do a 5K in so many minutes, then you double that and add a minute or something for what's your expected 10K time, right? There are rules of thumb like that. But this does, and it's really the anaerobic aerobic break. So there's a story for why that happens, right? That this is stuff we've got stored in us, we use it up. I'll come back to that for another surprising example in a little bit. And then now we're running on oxygen. And the 800 is sort of, well, you can see strategy in the 800, right? It's not always just a straight up thing. It seems that swimming slows down, it doesn't slow down as fast as running. Okay, so that's an interesting bit of work. 1K for running. Okay, so there are those pieces. So this is interesting, and it's one of these classic kind of breaks in scaling. We see that a lot in lots of different systems. There are two scaling regimes, and there's some characteristic scale in the middle for, which we should be able to explain, like why it breaks. Okay, so this is a few years later. This is for the 100 meters. It's the best time in the 100 meters, so this winning time here. In red are women's times, right? This is from, I guess it's from the Olympics, actually. Yeah, it's just the Olympics, which is a bit odd, right? That's not necessarily the world record, but it is from the Olympics. So you see, so this is kind of unbelievable. This is a Nature paper again. It's a one-pager. The extrapolation is simply linear, and the big story here was that in around 2150, women will be faster than men. So this is not great statistics because maybe that's going to be true, but at some point they're going to be sub-zero, which will be very fast. Okay, so anyway, they really stood up for themselves as the first author. If I'm wrong, come back and talk to me in 2156. So, good, well played. Yeah, interesting. Yeah, so these aren't all the real Olympic records. Okay, good. World records. So that's a bit of a shifty thing. Anyway, that Nature, let's publish it. Talked about this one. So I talked about this just briefly, but I wanted to show a few more slides for it. It's an interesting thing. So here's the claim, right? So the basal metabolic rate, and we'll get to maximum power in a second. We'll do that next. How fast can an organism run? So it's proportional mass to the alpha. And so you might think, alpha equals 1 should be kind of a maximum, right? You shouldn't be able to sort of have something, the energy you're using shouldn't be more than, proportional to your mass. That would be bad. It would be bad for biology. You wouldn't get big things. And it is lower, and I talked about how we might expect 2/3, which is a dimensional analysis kind of scaling, right? So volume or mass to the 2/3 should scale as surface, as long as, our organisms aren't really bizarre looking things, right? So this is not a spherical elephant, but which physicists like to assume, but they aren't growing in crazy ways. Snakes might be interesting. So people study this for now, going back in the 1850s. The original work was actually for a tobacco plantation in France, and they wanted to know how much to feed their workers based on their size, right? So they asked a couple of physicists, this is good times, Industrial Revolution, and how much gruel they should give everyone, or baguettes maybe, and they came back with this estimate. Well, if you have this 2/3 power, that should be it, right? Because that's sort of the energy you'd be giving off through your surface. So not good. But then people started to think about it in livestock, right? That became the early 1900s. How much should you feed your animals based on their size? And then there's sort of lots of elaboration. It turns out that prefactor C in that scaling, well, I've said that it can be quite meaningful. It does seem to, allegedly it varies according to these 4 main categories of organisms measures. Very harder to measure fish and whales and things like that, right? You have to, someone has to put an oxygen thing on the front of this platypus or something else, or watch how much it eats. This is a little slippery when it comes to some of the data that's gone into this. But I'm going to put these guys here because they're excellent. Their body temperatures are quite low, so their C factor is down. But they're special because they do what? These are very odd mammals. Well, they do a lot of things, but they are kindred and they lay eggs, right? They're the only egg-laying mammals. So they have a bit of a different game, right? And then you've got your hoppy ones and other kinds of marsupials. They produce a young that then sits in a pouch, so that's a bit of a different game. Birds have to run at a higher kind of energy anyway to do this crazy flying thing, so they've done a bit better evolutionarily, I suppose. And that's our team here, the eutherian mammals. Well, I'm pro-vertebrate. Okay. Okay, so that's interesting. But then dimensional analysis, as I said, is a balance of you're giving off heat through your surface, and if you look at lots of little organisms and scale them up, and you measure their surface area, which people have done in strange ways. I think with cows, they've used, like, they've painted them and counted how many revolutions of whatever, some sort of roller that you have takes to cover the cow. You can also remove the cow and kind of unpeel it. People have done that as well. People have done things like measure mitochondria by atomizing the organism in question, and you have a bit of char and you measure the mitochondria in your otter or otherwise previous animal. So there are lots of crazy things people have done. Okay, so that's, this is a very simple one, and this is not exciting, right? This isn't exciting. And we're not going to worry about this, but this is, if you want to go into physics, there's the black body radiation story. I'm just mentioning it. It fits quite well. We give off heat. That's how we can see each other with goggles in the night, right? Okay, but this is apparently so I'm going to call it the Church of Porterology. I'm just going to point to this. It's a thing for coconuts in the next semester. But this has been the prevailing belief since about the 30s. And it's kind of a weird Pythagorean thing because there were some measurements of exponents with slide rules and so on, crazy things, that had this number slightly higher than 2/3, right? This is just a 12th higher. So it's 0.72 or something in some measurements, and the idea was, well, it's got to be simple, so let's go up to the next simple fraction. So it's a bit of a strange thing that happened. And then it appears in biology textbooks eventually. It's just a truth that no one could understand. People invoke fourth dimensions, all sorts of madness, right? Because if this was d over d plus 1, and d is 2 for us, right? I should say d minus 1 over d, right? We're in 3 dimensions, so we get 2/3. If we're somehow in 4 dimensions, which is something to do with time. So crazy ideas, right? So that's very strange. Anyway, so this is a bit odd because this isn't great actually for biology because this is a higher exponent. It means that to make a bigger organism, you're actually going to run it. The motor for that thing is going to run, its base motor is going to run at a higher rate, right? This is power. Anyway, so that doesn't look good. People don't mention this much. There are lots of other scalings that people claim to be true. So heart rate decays as mass to the -1/4, right? So you get a little mouse and they tick, tick, tick. They're very fast. And hummingbirds, their heart rates are going crazy. And you get up to an elephant or a dinosaur, if you still have one, then their heart rates are much lower, generally speaking. There are time to so this is sometimes taken as age, right? But it's really reproductive maturity. That scales in a certain way. But if this is age and heart rate, then we have a nice story, which is on the second one. Average lifespan. Let's say it's some power beta, right? It's growing with mass. Bigger things live longer. And they also have a lower heart rate. This is not, I'm going to tell you it's absolutely not true. That's a quarter. The data doesn't support it, which is very surprising. And then the theories are all terrible. But this is a beautiful story. Poems get written about this. So the average number of heartbeats, right? So you want lifespan times heart rate. It's m to the beta times m to the minus beta. So, right, your elephant very roughly has 1 billion heartbeats, and so does your mouse if they get to live out a full elephant and mouse life. Roughly so. But it doesn't seem, whatever this power is, it doesn't seem to be super far away from that. Of course, you get things like cockatoos and parrots that live for 100 years, or tortoises, that are still around that Darwin brought back on a boat, actually. They're still just being a tortoise. And they're like, where is that Darwin guy? I want to talk to him. So that's quite a beautiful thing. Anyway, I just wanted to sort of point that out. Okay, Church of Porterology. Very strange. Okay, we saw these things. We saw this. This is a bad thing. Okay, then this sort of connects into, I should probably put this in the right place. So how fast do things move, right? So this is now about maximal power. This is not just hanging around resting. And these are charming kinds of papers because they get to put lots of silhouettes of things in. So this is literature search type work where they're simply looking through, searching for certain kinds of terms. I think I have another slide on that. There's some variation here, right? This is 2 orders of magnitude here, but this is 22 orders of magnitude in mass here, which is a little inflated, right? So mass, so that would, a length scale would be more like 7 orders of magnitude, but this is a vast variation. And maybe I didn't say it properly before, the McMahon and Bonner book from which I took these examples, size is the big piece, right? There are lots of things to measure about an organism, but your sort of first thing, you want to know if it flies and does all these things, but there's a big, big piece, which is just how much does this thing weigh, right? Gravity matters, all these sorts of things matter. It's got to feed itself. So a lot of things, it's very sensible to tie lots of things to mass, right? Sort of the thing to pivot around. Okay, so this story here is this is the maximum speed divided by the typical length of one of these organisms. And so the suggestion here is that maximum speed just scales its length, right? So if you've got an organism that's twice as long as this other one, its maximum speed should be twice as big. And it's not really, this is a bit different to what we saw maybe for weightlifting, which you had a 2/3 power. This is a bit of a different thing. And it's all sorts of organisms, swimming ones, ones that run around on land, also, and flying ones to some extent. Although we're going to put the struthiest birds in here, yes. Okay, so this is that's a nice problem to work on, which you have. Then and that paper was 2015. This is a recent, very recent paper. I added all this morning from this year, and this one is looking a bit differently. Now we're back to body mass, and we're looking at maximum speed. So I haven't quite squared these two completely, but the story now is that actually the fastest ones, the biggest ones, tend to be slower than you'd expect, right? So if this was a perfect scaling, you'd go up here, and your elephant would be up here. These great little drawings, and here we have, right? So we've got fish, we've got an octopus sitting in here. Penguin gets a run up to whales, but these guys aren't as fast as you would expect. So there's a very nice story that they've been able to put together for this, and over here, of course, we have birds, right? So running, swimming, and flying. Very different activities, but they seem to have a big story. That's just on one plot there. Okay, so why is that? And so here's the basic idea. I have some calculations on the next slide, I guess, but let's see if we can explain it here. This is the theoretical maximum based on their size. So if it just scaled nicely as a big power law, right? So bigger things did get faster and faster. So this is the theoretical maximum from a power law scaling for an elephant is actually here. And I'm not sure what this thing is, but is that that's a mouse for sure. Can you tell me what that is? That looks like some sort of dog or wolf. It's a little cryptic. I'm sure it's not a limpet or something. But anyway, so the problem is it takes a while for these things to get going, right? Which is why, yeah, right. So it's sort of surprising then for a very tall person to be very fast in 100 meters, right? Because it takes a while to get them going. But that turns out to be disproved recently, but just one sample. Okay. Okay, here's the problem. This is an anaerobic thing, right? So you've got this energy stored in you that you're just like throwing into the system to explode into this machine so you can run as fast as you can. But it runs out. And so the time for that to run out is such that it doesn't matter for a mouse, right? So a mouse will be able to wind up to its fastest speed. They get there very quickly, right? But the elephant, by the time it's kind of like getting going, it's deployed, all the energy's been dumped out, right? So it doesn't reach its maximum. So you've got to dope your elephants if you want to get them up to their speed. Need blood passports for these guys. Okay, so, and that's putting these pieces together, and that gives you this story here, right? So it could go much faster, but it runs out of gas, essentially, the anaerobic gas. And so this is a way of putting it all together, and in fact, they had a lot of fun. They threw some dinosaurs in here, not measured, obviously, but estimated from shapes and so So there are some nice pieces. We don't have to worry about this too much. I'm just sort of putting it in a slide. But this is generally how velocity is going to work in a simple kind of physical way. There's an exponential decay here so that you get to your maximum velocity and it's approaching with this exponential decay. So that's fine if you're a mouse, you get there really quickly. But if this k is such that it's a slow decay for an elephant, then you don't quite get there because there's another piece here which is, I'm going to put it here. I'm not sure if I wrote the acceleration time in. Yeah, here it is. This is the amount of time you've got, and this scales as some mass to the power of g. It's a pretty big range, as you can see, but there's some time that it runs out in. You can put these things together. We're not going to worry about it too much, but they do very well in being able to show this deviation from scaling at an endpoint. So that's often true, right? One end of the scaling, something will fall apart. Like for earthquakes, it's the thickness of the Earth's crust.
Is this the same as if you were to dress up at one species?
Look at what again?
Like one species? Like
one species. Oh, you mean like bigger versions of them?
Yeah.
Yeah.
If you were to look at like humans, like across the whole thing.
Yeah, so you don't get enough scaling. You do get some intraspecific scaling. You get a little bit, but it's harder to test. But something like cats or where there is a decent range, it does seem to fit. Yeah, even within them. There are some things that do scale differently within species. That's another piece. But yeah, but again, you don't have enough. You don't have a huge range. But that's a very good question because people have got worried about that a lot. Yeah, maximum speed escape. I mean, this is what they did, right? They searched through lots and lots of data, which is actually in this case papers, and drew this stuff out. Okay, so that's an interesting thing. You have to be quiet. You have to do a good job to clean up the ends of these things. Here's another pretty good scaling. This is back from the McMahon and Bonner work. So this is engine in mass, kilograms. So these are engines that humans have made, right? We make a new engine. They're not all just scaled up versions. Sometimes we have to introduce a new technology and so on, right? As we move up in power. And so this is brake horsepower, which is basically power, right? That's growing as mass to the 1. So this is well, I mean, organisms roughly do this. I mean, we had those slides just then. But the RPMs involved actually decays in a particular way, and so this can be figured out as well. What this means is, you make an entirely new engine, and it's the same with Moore's law. You make an entirely new kind of transistor sort of technology. It still appears to be that it still will fit on this kind of big governing story, right? So biology, evolution's working there. This is engineering, making things based on what's come before. There's a lot of evolutionary type stuff there as well. But there's a big kind of envelope in which you have to fit, right? So these scalings give you these big stories that shape what's possible. The details are weird. So again, this is another example. Seems very small, but we're kind of moving into mechanical things now. These are an example of nails, and these are nails that weren't made by computer. These are made over many years, hundreds and thousands of years by blacksmiths, sort of making nails that work pretty well. They don't want to use too much material. They need to be able to function well. If you want a nail of a certain length, then what do you do with its thickness, right? You can make it too thick and then it's not going to go in well. If you make it too thin, then it will buckle. And so it turns out that there is a characteristic scaling, and here it is. Here, this is length here, and this is diameter. So diameter, it's that slope there, 2/3. This is just a guide to say it's proportional. It's not scaling isometrically, right? So if length and diameter were isometric, like a little nail, you just blew up the picture, it was the same as a big nail, then we'd follow that line of slope 1, but it's actually slower, right? So the diameter gets, as you double the length of a nail, or go to a nail of twice the length, you don't see a nail of twice the diameter. It grows more slowly. Trees seem to do something opposite, right? Trees sort of standing up, they get thicker actually as they get taller, disproportionately. You can play around with this a little bit. Diameter then is scaling like mass or the volume of the whole thing to 2/7. Length will have to scale as mass to the 3/7. So we're going to have, for the whole piece, we're going to have diameter squared, right? That's the cross-sectional area, pi d over pi r squared. So it's basically proportional to d squared. So there's a 4/7 for that, multiplied by length, 3/7, so 4/7 plus 3/7 is 7/7. So this fits, these things fit. So this is a perfect example of allometric scaling, right? It's unusual, peculiar scaling. And again, these are nails that people made over time, right? They're worried about material, they want it to function well. So that's, can you do a back of the envelope thing? And so here's a quick piece to sort of potentially explain it. And you need material from other places. That's often the case. And in this case, you need to know that columns. This is a result from mechanical engineering and from some very smart people like Galileo, that they buckle under a load. So the force of the load will depend as diameter of the fourth divided by length squared. Right. So let's get this piece right. Yeah. So if you make the length higher, right, then you need less of a load, right? If you just make a longer nail with the same diameter, then it's more wobbly, right? It's going to be a wobblier kind of thing, and you hit it, it's going to have more of a chance of buckling. If you make the diameter, as you increase the diameter, you get a nice returns to that. It goes up as power of a fourth. So then there's this is the back of the envelope nonsense, right? I'm not telling you have to do this, but this is a clever thing, that as you drive this nail in, there's this resistive force being applied, and it's going to be proportional to the diameter. And you want those things to roughly match up, right? So you want it to be the case that the nail will work, but it's just, this is true. Nails do buckle if you don't hit them properly, right? They're kind of on that edge of things, which can be frustrating. I remember my grandfather showing me how to fix them up. So we're just going to put those two together. And so that's pretty simple, right? There's a d to the fourth divided by L squared proportional to d. We bring this over here, we get a d cubed. L squared over here, so we have d cubed is proportional to L squared. And then we can take the cube root of each of those, and we'll get d is proportional to L to the 2/3, which is what is seen empirically. So it's a nice little just so argument. Galileo actually noticed this. Euler thought of these things as well, also a very smart person. And this is McMahon and Bonner, that's where this book I've been talking about, but McMahon has this paper in Science in 73 that talks about this too. Okay, so this one is in your assignment, I think. And it's a very peculiar, it's very weak scaling, not a lot of size variation, but it's sort of a peculiar kind of fun one, right? So this is again a performance one. This is speed, and this is the number of people in a boat, right? So this is rowing. So 8 being the biggest one. Don't have dragon boats or anything like that in this. These are performance-based things. It depends a little bit on whether you have sculls with a coxswain or not, right? I played cricket, so we look down on the rowers who look down on us in a different way. But I did feel bad for the coxes. They seem to be somewhat tortured by their rower people, but they would torture them back. So it was a weird relationship. Anyway, so but this is a very weak scaling, and it's to a power of 1/9. If you run around saying, "Oh, I found a power of 1/9," it's probably 0, right? It's probably logarithmic scaling. But there is an argument for this based on fluid mechanics. And again, the work you will do is really just algebra. But that's a cute little one. Probably should be in a different place. Okay, so the scaling in all sorts of things. So this is for gravity, Coulomb's law, right? So the force of gravity between two objects, large objects, is going to be mass 1 times mass 2 divided by r squared, right? There's a gravitational constant out here. So this is very much a 3-dimensional story. This 2 is d minus 1, right? This is where d is 3. Because we're talking about the shell around an object. So the force coming out, if we just think of the force from gravitational force from one of these objects, then and this is a funny thing. So it's decaying as 1 over r squared, right? So it's being thinned out through this shell. That's the amount of gravitational force is sort of constant if you multiply by the shell, which has a surface area of 4 pi r squared. So Newton actually, if you look back in his work on this, he tried all sorts of things. He had r to the 4th on the bottom. He had lots of other things he was messing around with. It wasn't an obvious thing at all when he wasn't working on astrology and crazy things, and eventually making money. So yeah, but it has a sort of a nice feel to it, but it's not obvious. Okay, so that's the dimension of a sphere's surface. And partly I introduced it because it's just sitting there. It's a nice scaling thing. But we'll actually see it for people as well, which is odd. We live basically in 2 dimensions, right? We go up and down elevators and things and mountains and stuff, but we live on a pretty flat surface. So if you think about cities moving stuff between cities or whatever it is, then there's a kind of a gravity law, but that gravity law will be d equals 2. So we'll see a 1 over r for that, which is interesting. Okay. All right, so a lot of the back of the envelope stuff is just messing around with a few things, and then you're trying to get whatever, we had this gray matter versus white matter example, so you could mess around with that. But there is a principled way of doing it, and that's what this piece will be about. So it's a very famous paper from 1914, so the Buckingham Theorem, and you can find all sorts of stuff online about it as well. But I'll give you the basics here. So I remember hearing about this, and I went off to photocopy it, and because this is what you used to do, right? A long time ago, you'd actually have to go to a library and sit there and just photocopy things. But this was pretty brutally, this is tape. It was still there, but it had been well photocopied by that point, well used. So that's always nice. I did have one experience once where, and I tell you this is like the time before the web did exist, but I remember going and I find this paper I'm looking for. This was at Columbia, and I'm spending, you've got to find the right place, and then there's success, you pull out the thing, and someone had ripped that one out. It's unbelievable. I mean, just the humanity. Anyway, I'm still pained by that. Anyway, so extraordinary thing to do. Okay. Oh, Stigler's law of eponymy. We'll get to that. That's very enjoyable. Okay. Which means it's not named after the right person. Right. Nothing is ever named after the right person, including Stigler's law of eponymy, which is very good. Very, very sneaky. Okay. We'll have more examples of that too. Is this alive? Beep. Okay. Okay, so here's I mentioned this the other day. Here's the basic observation is you have an equation of a system that's, this true equation. It can't depend on the units, right? It can't matter if it's meters or yards or kilograms or pounds. So let's imagine, and it's going to be a little bit, and I'll give you an example involving a pendulum, which is kind of a classic example here. But we'll do a little bit of abstract stuff. So we've got a bunch of things, right? So this could be velocity, could be period of the pendulum, could be length of the pendulum, mass of the pendulum, something like that. And we want to know, is there some sort of equation that connects them together? And we're just putting 0 here at the end. But basically, we want to know, is there some sort of equation that relates them together? Some sort of conserved piece. And if there is, then it cannot matter what the dimensions are. So this is a very simple, maybe dangerously simple example, which is just the area of a square is length squared, right? And if we think about squares, and we think about squares of different sizes, and we look at them, we think, well, there's really only one thing that matters, right? There's length. And it's the same for circles, right? We can choose different things. We can say diameter or whatever we want, but we know, if we've got one of these. So straight away with this, we can say if we want the area of a circle, we actually know that area divided by r squared has to be a constant, because it can't matter what these dimensions are. So if we measure area in yards and then radius in yards, then the yards will cancel out and we'll get our constant. Right? If it was in meters, they would cancel out as well. So that's the simple observation. So what you do is you take your system and you create all of the dimensionless arrangements of parameters that you can. And then your system can only depend on those dimensionless things. Right? You can't have an equation. Obviously there's this version here. There's units of length squared here and units of length squared on the side. That's fine. But if we want to clean it up so it doesn't have any dimensions, then the only things that can go into that equation have to be dimensionless pieces. All right. So we're going to take our n independent dimensionless parameters. We're going to take our n parameters and then rewrite them as p independent ones. That's like a little parenthetical remark. Where p is the number of independent ones. And so we'll rewrite them. We'll take all these q's over here. They're going to be pi. This is terrible. It's not pi. It's not pi. Just use pi. I don't know why I use pi. It seems very bad to use pi. Pi should be just pi, and that's it. But used, that's the notation, and it's called the Buckingham pi theorem, so kind of stuck. Yeah. Anyway, so then we must have a function that only involves these dimensionless pieces. So our example here is very simple, right? So a over L squared minus 1 is 0. And so we'd say pi 1 is a over L squared, right? I mean, we could have anything. We could have a squared over L to the 4th. That works too. We can do silly things. But, you know, we'll clean it up as well as we can, right? So so this doesn't, we lose the physics of the thing when we write it like this, but this is a dimensionless version. Right. And we can always, we have equations, we can always put a 0 on one side, right? We can always rearrange things. So we've got a 0 on one side. So this is a very general kind of form, and then this is, a sort of a best form. Okay. Well, we'll use some other things. Okay, so here's our example. Pendulum with a platypus. And we're going to have, it's just going to be a very, just a mass just sitting there. There's going to be no air friction, all those horrible complicating truths. So what are the things involved with it? It's just swinging back and forth. We kind of have this idea. We know the pendulums do this. We build clocks around them. So we're going to have a mass at the end of it. There's gravity. There's the length. And then there's the period. Right? So acceleration due to gravity, I should say, and pendulum's period tau. So these things, there's time in here, gravity, right? It's length over time squared, mass, and length, right? They're the units, right? So this thing's going to be measured in kilograms. This is going to be length over time squared. This is going to be time. This is going to be length. So there's an interesting thing you can see straight away from this. That was maybe too elliptical, but let's do this. Okay, so here are the variable dimensions, and this is how we indicate the dimensions, sort of a physics notation. And seems odd, this is the variable, but this is sort of a universal thing saying length, right? Its dimension is of type length. And it's of type mass, of type length over time squared, and of type t. So our equation, so if you look at this, there's one thing that sort of sits out as a bit odd. Anyone see anything?
Is it gravity being related specifically to the length of the pendulum?
Right, so the only way to connect gravity to anything else, so this is good, right, is going to be through this one. That's the only thing that we can combine gravity with. True. I wasn't really asking a very good question, but you're right. And then what about time? This one, tau. That can similarly only be related to this one. This one. How do we clean it up? So which of these ones can we use to divide through here and get rid of mass? So we'd like to, just as we did, say, for this example, well, I guess I have it here, right? Area over r squared, sorry. Yep, area over r squared, right? So this is a length squared on top, could be yards squared, and then we have yards times yards on the bottom. So they would cancel each other out because that's what we're trying to do. We're trying to get rid of all dimensions. We want an equation.
Mass is just a basic
Mm-hmm.
variable.
So how do we, it is, but we want an equation that doesn't have any dimensions in it, right? So if we have mass sitting in there, it's going to be in grams or something like that.
Isn't an ideal pendulum the mass doesn't?
Right, so that's true. So we can get to it from other directions, and that is absolutely the observation, is that the mass doesn't matter. It doesn't matter how heavy this thing is. So our dimensionless, the only way we can combine this is to have mass to the power of 0. Right? There's no other way we can deal with it. So our equation that's going to relate these 4 things together will not have mass in it. So mass is, it doesn't matter what mass is. which is interesting, right? So we're going to connect gravity, the gravitational acceleration, to the length of the pendulum, to the time of the pendulum. And they're the only things that can be involved in this dimensionless equation. All right, so these are words, that I'm sort of throwing up here. You can come back and read them. So as we said, we're going to find all the independent combinations of these parameters. So in this case, it's mass, length of the pendulum, the period of the pendulum, and the gravitational acceleration into these pi1, pi2, pi p. And then we'll have an equation, right? So let's see, how do we do this? You can just do it sort of as we did now, right, just by sight, but if you've got 130 of these, then it's harder. So we're going to say, well, maybe we'll have, we're going to have at least 4 of these things. I mean, at most 4 of these things, but let's just take one and sort of a general kind of notion of one. It's going to be Q1 to the power of some power, Q2 to some power, right? There's going to be some powers of these things put together that gives us a dimensionless piece. All right, so we want to find which powers do that. And so we'll take dimensions of this equation, right? So what are the dimensions of our pi? We want them to be 1, right? That's the way we write this. If it has no dimensions, we use 1, right? So the dimension of 3 is 1. So it's going to be the dimension of what this thing is, dimension of this thing, dimension of this thing. So I think we have our example. So for the pendulum, the dimension of the first one is just length, right? This is the length of the pendulum. The dimension of the second, which is the mass of the platypus, is just m. Dimension of gravitational acceleration is length over time squared. And we get a t for time for the period. Right, so we're going to put all those pieces together. These are the, right. So if we put those things together, so the dimension of this thing is going to be length to the x1, mass to the x2, right, because these were just simple. Then we get length to the t minus 2 here, to the x3, and time to the x4. So we want to find the powers that will make this into, balance all these things out, right? The lengths will cancel, the mass will cancel, the times will cancel. We want all possible ways to do that. Now we're going at some lengths with this simple example so you can see how to generalize it. So we're going to put things together. There's a length to the x1 here. There's a length to the x3, so we get x1 plus x3. Mass is by itself, as we talked about before, just that one. And then for time, we get t to the minus 2x3 and plus x4. So what we want, excitingly, is that this has to be 0, this has to be 0, and this has to be 0. It means they all balance out. So we can see what the answer is for this one. This is the thing we talked about. Mass can't be involved. But there looks like there's going to be a couple of combinations here. So what we want is this, right? We want x1 plus x3 equals 0, x2 equals 0, and minus 2x3 plus x4 equals 0. That should be equal 0. Does anyone have any idea what's the mathematical thing that we do next? What does this look like? It's a system of equations, yes. Right. From which, so which magnificent field is that? Linear algebra, right. Matrixology, yes. Good. Okay, and this is actually a null space problem, right? Because this is a combination of things that they're sent to 0. Okay, so you write everything down. I mean, this is actually pretty easy to do. You just say, I figure out my dimensions are, then raise them all to the power of these x's, write all of this down, regroup everything, and then peel off all the equations, and then write it out, right? So we had an x1, x2, x3, x4, and this is the first. This is associated with the length, right? So this is the length dimension. We have to have these two things adding to 0, so it's x1 plus x3. This is the mass dimension across here, so that's just x2, and this was the time dimension, minus 2 times this one, plus 1 times this one. So it's a null space equation, right? It's a matrix times a vector equals 0. Sorry, it's just a joy. And if you want, you can know these things, right? So the number of dimensionless parameters that you end up with will be the dimension of the null space. which is, if you know from these things, right, is n minus r, right? So the shape of this is m by n, and where it's the rank of A. And so, in fact, we can see the rank of this thing, right? You couldn't reduce this any further. The rank of this one is 3. So, in fact, you can figure out, so this is funny. We turn the number of dimensionless things will be the dimension of a null space associated with the problem. Very nice. Okay, so we know that there's just one dimensionless variable. So we're going to end up with an equation like this. F of some blob is equal to 0. So and that means that that thing has to be a constant. I mean, it could be sines and cos or something, but this basically this has to be a constant. You have to be a little bit careful with that. This is just saying what we did. You can come back and read that, but that basically just says exactly what we did. And you can find you can figure this thing out, and so that's one of the problems. Pi 1 is in fact, and so it could be a flip of this or some other thing, but length over gravity times tau squared has to be a constant, which is groovy. And if you invert this thing, you get that the period is proportional to the square root of the length, which is kind of a classic result. I mean, very much a classic result in mechanics, a simple classic result. But you can get to there through solving the whole thing, right? And F equals ma, and you get the whole behavior, and they sort of dig that out at the end. But this is sort of a nice way to get to that. All right. Okay, lovely, very nice. Matrices. Okay, so you could do this. So there's an example where someone could just sort of sit there with a pencil and paper and not solve differential equations or anything and get to that, and enjoy matrices along the way. So this is Barenblatt's got there are a couple of books by Barenblatt. One's simply called Scaling, and they're beautiful things. I'm not if you want to look into this more, quite fantastic. But this is a classic example, I keep saying that, a great example from that he highlights, but is well known in science. So Taylor was a fluid mechanics guy in England, and he looked at so this is 1945. This is a dire situation. This is the nuclear, the Trinity test in New Mexico. This was published, I think, on the front page of Time magazine, right? The picture of this thing. And they put in times for, so it was this sort of sequence photograph, and they put in times for where the blast had got to. So this is a top secret thing, obviously, but some of it was let out into the public. And so he's sitting there having his cup of tea and scones and figures out how much energy is in this, just from this one picture, which is insane, but he did it. So somehow they spilled the beans on this one. But it's one of these CSI type ridiculous things, where they see all these things. Okay, just looked at it, right? So I guess there's a scale for meters, Empire State Building to help, and time, and just thought about it, right? So this is not very few people in the world could do this, but still, it's a great achievement. Length, time, these things matter. The density of the air outside, so the density is mass divided by L cubed. The energy in the explosion, which has the dimensions of mass length squared t squared. You can think about it in different ways, but half mv squared if you like. So that would be is the v squared part. Four variables in 3 dimensions, which again you could do the Buckingham pi thing, or you could just play around on your napkin, and you figure out that there's really only there's only one way to combine them to get rid of everything, because there's a length, a time, a mass, and a mass here, and you want to get rid of mass, you want to get rid of length. So there's only one way to put them all together, and you get this, that the energy of the blast is proportional to an odd thing, right? Radius to the power of 5 over time squared. And figured out that the speed decays is 1 over r to the 3/2. So that was all just by looking at one picture. So it's a famous example of figuring out something ridiculous, I suppose. Anyway, so Radiolab is a very confounding thing to me, because half of their things are terrible and kind of bad. I don't know how you feel about it. Maybe you never listen to it. It's a podcast. But some of it is absolutely amazing, right? So we'll listen to one piece later on. This one's on elements, and it's about how nuclear blasts left imprints in people's cells, right? That was just there for decades afterwards, and you could do all sorts of things based on that. It was basically an unfortunately strange natural experiment. It wasn't, I mean, obviously it harmed people near these things, but for a lot of people, just they had this little marker in them. Okay, that's a piece. Another Radiolab one here. This is odd because we've been talking about units. This is a very strange thing, and when I first heard about this, I thought it was not serious actually, but we're slowly getting there. It turns out that we have these fundamental, right, there's the mole, the Kelvin for temperature, right, there's numbers, and then we have angstroms, I think, is that what that is? And so for mass, we have kilograms, right? Time is over here, seconds. And this is the way it's being worked out, is that to determine the sort of these pieces, there's actually a problem in that kilograms, there's a real kilogram. There's just a kilogram that we say is a kilogram, and it's in Paris. And this is very problematic because you've got to look after it. So of course they do look after it, and at some point they cleaned it, and it took a grain of sand off it basically, because they'd made copies of it. So you make copies of it. So here's the original one. We're going to make a copy, weigh it very incredibly, ridiculously carefully, and now we've got a whole bunch of copies. We believe in them, and then they cleaned the original one, and it lost about a grain of sand. So this is not good because everything depends on this anchor. So that's what this is depicting here, is we have this kind of anchor that's just, there it is. It's over, that's the kilogram, which is really silly. So there's been a very slow push to get this sorted out, and it matters actually for real science at small scales and at large scales. You get errors based on some problems here. These things will depend on natural phenomena as they have, like the second is like a decay of a cesium atom, right? So you write down the recipe and someone else can go and measure it, right? So you can say, okay, now I have my second, and it doesn't depend on you, right? But here it is, kilogram, right, in a jar. Actually, so Radiolab did a nice, and they did that. I mean, they could be condensed into like 3 minutes, but anyway, it's a fun piece. But here are the strange things now. We're going to say Planck's constant is just some number. Everyone's fighting about this x here, but it's going to be, it doesn't go on forever. It's just going to be there. It's not as bad as the Indiana town in the 1800s where some doctor said we should make pi 3 and tried to put a bill forward and got a fair way because he could square the circle and it would solve all sorts of problems. Did not get voted in. Anyway, so, but then this is weird. The meter is chosen so that the speed of light will be this, which seems odd. But this is just, people have been thinking about this for a long time, and there's a Radiolab piece, and I guess that's what it is. Yeah, less than or equal to a kg is the title. Yeah, that one's not too long. That's quite enjoyable. Okay. All right, so we're going to get through this. All right, so, but that's really weird. I just want to say it's really weird. You'd think we'd have the units absolutely solid, but here we are having arguments about it. And it has to be by all governments and all the agencies around the world of different countries have to talk about this. So it's very complicated. Okay, so this is Lewis Richardson. We will come back to this character who did all sorts of things, but it has a number in fluid mechanics named after him. I think gave up on science because everyone was terrible and crazy and went off to become a headmaster somewhere in the backlands of England. But before all that, he did lots of interesting things, and one of them was to sort of assert that we have a bunch of people solving differential equations in rooms. We could predict the weather, right? So he kind of presaged the whole idea of computational work. And he has this nice little quote about turbulence. Turbulence is this area of fluid mechanics where there's incredible scaling. It's based on Swift's little thing about fleas, which are sort of fractal stories. But I just want to point out this is another one of these great back of the envelope calculations. This is an aside. Turns out that in some of Van Gogh's paintings, there's a turbulence type aspect if you look at the way luminance is correlated across the painting. And it was only when he was not well did he produce paintings like this, and no one else seems to have done it. Okay, that's a fun paper. But you would think it has nothing to do with turbulence. But anyway, so this is Gaurav, who's an incredible genius, did all sorts of things. Again, with the envelope business, figured out that the energy in the wavelengths of a certain wave number k decayed like this, right? So there's a energy dissipation term, and then there's this k to the minus 5/3 is very famous. So it's the same kind of thing, just saying, there are only a few things matter, and they can only be combined in this way. This has really sort of been this is 1941, this has been, because turbulence is incredibly difficult to understand, right? Fluid mechanics basically kind of breaks down. It's messy, but it matters a lot, right? You fly through turbulence, maybe in a plane. It's very damaging to buildings and all sorts of things. But it's a hard thing to understand. But this was sort of this great leap forward. And you get energy sort of distributed across all sorts of things, right? The bigger scales, the smaller scales. And there's no internal characteristic scale to it. The thing about this is there hasn't really been a giant advance since then. Maybe Pixar will figure it out with their little froth and stuff that they can produce. But it's hard. It's very hard to simulate it. It takes incredible computational stuff. Anyway, that's just to sort of show you the thing. Okay, fractals, of course. Lots of scaling in fractals. Again, this sort of anomalous scaling. I think this is a broccolini, I think it is. Okay, there's a paper in Science about this one. So there's, mathematicians have very much enjoyed the fractal story for a long time. Big question is, how do you get them? How do you get these self-similar structures, right? And so there are origin stories for some of them, but not enough. Probably the first place, and so this connects to the work I've done, self-similarity of river structures was actually the first, seems to be the first area where anyone quantified this properly, like how the bigger channels connected to the smaller ones in terms of their size and length and so on. Hurst, this is roughness of time series, thinking about financial time series and all sorts of things. Hurst exponent is a thing, actually, which talks about the roughness of something. Again, this is Richardson, who's doing something completely different now, thinking about coastlines. So he has I think Barenblatt has the famous paper, actually, but both of them were thinking about this. How long is the coastline of England, was the question. And it depends on the ruler you use, right? So that was a sort of a great example of this. Fractal diet. Barenblatt, who passed away a couple of years ago, introduced the term fractal, and he really found them everywhere. But it built on this work here. Okay, so I'm going to talk about that's physical things. We'll talk about people a little bit here, and then see how far we get. Okay. So Luis Betancourt, who's now, and I mentioned their work. I showed you the walking speed as a function of city size, which was a little dubious actually. But now we're going to talk about what I think is an overall pretty great paper, and this is back in 2007. It's the start of a new body of work looking at scalings of properties of cities. And so, difficult thing to measure, but we have proxies for them. So crime levels, fair enough. Wealth, infrastructure, how many, so roads, right? Cables, wiring basically, gas stations, all sorts of things like this. Disease levels, how much energy is used by a city, how much energy is used by individuals, and then, because there's the individuals, right? How much a person uses in their apartment, say in a city, or versus what's being used to keep street lights on, right? So there's sort of some stuff going into just the city. Most of the work seems to be about, with respect to city size, and I guess I'll mention that again, but density isn't really included in this. Okay, this is the one I showed you, and I was saying it wasn't very good. There's the exponent here, b, right, 0.093, basically 0. But these are different, right? So these are wages. There's a 1.12 up here. Questionable, this looks like natural log, which isn't great. Population of city this way. This is super creatives, which is a little bit of a funny thing to define, I suppose, but it's about companies that are super creative in some way. I should look up exactly what they said by that. In fact, it's not in the paper. It must be in the extra supplementary material. So you see these scalings, 1.12, 1.15. These are super linear, right? So you get bigger and bigger cities, these quantities are growing faster than linear. It's not just adding people up. There's something happening as a function of more people being together. So it's sort of a network interaction story. This one is, wow, this is the heartbeat thing. I love that. Okay, let's look at some other pieces. So it turns out there are 3 broad categories of scalings. So the breaks are here. So these are these exponents, right? And these are confidence intervals. 1.16, this one, these are all, you see the bottom of the 95% confidence interval is about 1, maybe a bit shaky. But all of these pieces are kind of social things. Right? So there's disease actually, crimes, right? These are social aspects. Wealth here, things like patents are at the top here as well, just the number of inventors. Right? So you double a city, so you go from one city and look at a city of twice the size. You don't just have twice as many inventors, you have a bit more of them, which is odd. However, on the other hand, you get, or two other hands, I suppose, consumption by individuals of, say, water, electricity. These things are scaling more linearly, right? So people are still people here. But the amount of stuff to look after them, if you like, so gas stations, actual road surface, hard thing to measure, these scales sublinear, right? So bigger cities have a return to scale. I mean, it's interesting to look at this, these kinds of results, and this is 2007, so there's been much more work since then. But to try and figure out why do people end up in different places, which is something that's always been interesting to me, coming from a place where there's right? We always thought it was the greatest place in the world, like why would people move there? But that can sort of, it's hard to see, like, why do people end up? I mean, historically, there are all sorts of reasons with migrations, bad things happening and so on, but at any point in time, why do people move? So, all right, so the big story is the global supply things have a sublinear thing, so the returns to scale for infrastructure, which sounds great. Individual things scale linearly, and then these social quantities tend to go up superlinearly. Density doesn't seem to matter, which is weird, because if you go across population size and then look at the area that an agglomeration, which is a better term for it, right? There are weird definitions of cities, there's the political ones and so on, but what you see from space, then there's two orders of magnitude variation, right? So you have cities that are really tight, and then cities that are really spread out, kind of at all scales, right? So small ones and big ones. But that doesn't seem to be in their results. So this is a paper that it was just, this one. Yeah, so I added this one too. So this is urban scaling and its deviations. All right, so what we can do now is say, well, let's compare New York City to Burlington, right? Because we're going to use the scaling that we figured out for all of them and then collapse them all back down and see who's kind of above and below that scaling. Essentially looking at residuals, right? We're just looking at how far off this fit you are. And we're not just making linear fits anymore, we're making these parallel fits. Okay, so here's just a plot from their paper, just one example. So it's an interesting one. So we have, this is population here. This is wealth, right? What's GMP? It should be product. What's M? What is M? It must be gross metropolitan product. Okay, good. Okay, so what we can do is we can collapse, right? So you look at all of these little residuals here and then bin them. Okay, so we see this nice plot. This turns out to look like they fit this with a Laplace distribution. It's not incredibly important, but they fit it with a Laplace distribution. Okay, and then we can look at residuals and see how everyone's doing. This is for income. So Bridgeport, Connecticut, right? These people work in New York City, make lots of money. These people probably have, they're retiring there, Napa's here, Boulder here. So these ones are all doing well with what you expect, and then these places are not doing as well. So you can sort of, this is a way of actually reasonably comparing across scales, right? You're not just comparing to a city of the same size, which is a start. You want to do that as well. So cities of your size. This is a way of comparing cities of all sizes to each other. And actually, for patterns, Burlington pops out there. So, I mean, just a few of them are highlighted, but that's good for our team. Yeah, surprising actually. I think Vermont has the highest kind of startup some number like this, for innovation sorts of things like transfer, kind of out, innovation transfer out of things, because small places tend to be on the edge of things statistically, can be. Okay, so that's So this, this gives you a way to kind of look at things in a deeper way. Yeah? Question? No? We're nearly there. So this is again Luis, who has this paper, and this is something that I personally haven't had time to dig into, I admit, and I've tried to run it through people here in the class. This is an attempt to explain it, and it is about how people interact. Lots of other little scalings go into it, but the thing that he claims is that these scalings are 1 and 1 plus a sixth and 1 minus a sixth, right? That there is, which is all very nice. So I'll call it sixthology, but there's a 5 6 and a 7 6. So this is social, this is infrastructure, and this is humans, right? Which is remarkable if true.
What was
The one?
Yeah.
Yeah, so these are scalings. These are, so this is beta, if you like, social, and beta of sort of individuals, right? So things like, how much electricity does a household use? And this is beta of, say, infrastructure. Now, you know where you're trying to get to, right? When you write, I mean, he's a great guy. He's a very smart guy. You know where you're trying to get to, so maybe you get there, but through some dexterous envelope work. But I think the jury's still out on whether all this holds up. Okay, we'll get to this later on. Maybe halfway through the course. This is a very interesting piece. I've mentioned it obliquely, I guess. This is now looking at population density here and then facility density here. So this is, you take sort of a chunk of area and you look at how many people live in it. So that's the idea, right? So we maybe take the US and break it into square mile pieces, very dense in New York City, no one in Wyoming sort of thing. And then at the same time, look at the density of some facilities. And so this is on the left, this is ambulatory hospitals, and these are public schools. So very different scalings. I mean, it's pretty rough and messy, and maybe this deviates here as we get to larger populations. But this is more like a 2/3 scaling. I mean, you do bad things where you guess things based, like, d over d plus 1 makes some sense. If d is 2 dimensions, we have to walk to school. And then this scaling is much, this is much higher, right? So this is the sort of thing where there are 4 Starbucks on the same block, right? They're opposite each other because they're trying to get people in the door. They're not trying to service humanity. They're trying to make more money, right? And whereas something like a public school system is set up is trying to make, say, the average distance, or say the kind of burden incurred on people to get to that school to be as low as possible. So that means you're going to spread them out a little more. You're going to cater to people who live in sparser areas. Starbucks is not going to open up a place in the middle of nowhere, right? Unless they're feeling very generous. But these are 2 densities now, and this scaling. So this is something that's evolved over the last 10 years, but people have been looking at it back in the 1950s and 60s. Geographers, mathematicians. It's a very interesting feature of real systems. Very different thing again, right? So this is people. This is, there's more about war that I'll talk about later on, but this is about actually IED attacks in Afghanistan. And what you see typically is this crunching in time, right? So it gets shorter and shorter. So there's a first attack, a second one, and so on. It's going to be stochastic, but this is the difference in time between those attacks, right? So that's the difference between the first and second attack, the second and third one, and so on. This is on a log scale. Again, a log scale here, and it's getting shorter. And so, and then so here's the general scaling, right? So there's some initial time. This is the number of things that have happened, and then this scaling exponent here, which is called the escalation rate. So you can measure that for different places. You can see how it's moving backwards and forwards. Depending on which team is winning, because it is a game. I mean, a horrible game, but it's a game involving 2 sides usually. We actually have a paper on drone strikes where, and it's no surprise, I suppose, but these statistics disappear completely. This is with Neil Johnson and myself and a student who was in here. The team with the drones just does whatever they want, right? So there's no way to respond to it. But you see learning on both sides, and this is very much like organizational learning, right? So the theory of learning curves and all that sort of stuff is in this as well, which is rather perhaps surprising, but not really. Maybe this would be good to maybe explore a little bit next time, but it's XKCD, and it's kind of the only one I have on money at the moment, but it goes from all the way from dollars to trillions, and what those pieces are, what that money is associated with, right? So this is a scaling story. This whole blob is here in this little rectangle. This whole blob is here in this little rectangle. This one and this one. There is I should bring up one piece, because he does a good job to try and explain everything. So bad. I shouldn't do that. I think I should just do this. Yeah. Yeah, I mean, it's very thorough, but this was always enjoyable. The economic vortex, all this money flows in and out and out of and between households, corporations, and governments. This process is complicated. Anyway, so that's one to dig into. Money, scaling is unbelievable in money, of course. So many more things to tell you. Here's a weird one. This is language. And I guess I'll get to technology on Thursday, but let's do language. We're going to get to Zipf's law, which is a beautiful thing and appears in lots of different systems, but that's something I'm not going to talk about just here, but essentially you do this for cities as well, right? So you take, in a book, you take the word that appears the most, and then the word that appears next most, right? So it's the and of and so on. Count up how many times they appear, and then just order them, right? So rank them, 1, 2, 3, and then put their sizes, how many times they appear. If it's cities, you put how big the cities are, right? So the first city is here, its population, and then order them. You can do it with lots of different systems. And that tends to have a power law decay, right? A scaling kind of decay. We'll get to that. The reasons for that are kind of interesting and wonderful and complicated, but that's called Zipf's law. Anyway, that's sort of the big story really for language. But this is a different piece I just want to point out, because there are lots of scalings in language, lots of patterns. So this is about irregular verbs. This will be good. This is about irregular verbs regularizing over time. And so they had data in this case from Old, Middle, and Modern English. These are number of irregular verbs that are left of a particular frequency, right? So, well, let me just show you this. This is the transition between the different, from Old to Modern, Old to Middle, and oh, I guess they do that. Yeah, Old to Modern, maybe that's wrong, but anyway. This is the frequency of the word, right? So how often it's used, and this is its rate of regularization. So basically how many became regularized. So words that are used infrequently tend to get regularized more often, right? So this is the sort of way kids make a mistake, right? I buyed the thing. And it's about past tense. When you tell them that's crazy, you must say I bought it. What is wrong with you? Like we have a very strong response to people, getting language wrong, right? You is just sort of hurts. But this, so there's a nice, the rates are relative, but there's this nice decay here, right? Which is interesting. So it decays as f to the minus a half, it seems, of the frequency. What this tells you is words that are very common, and we have, to have and to be are our most common verbs. It's going to take a long time for them to regularize, but they've been dying out. So this is language as code, right? We are collectively cleaning it up and making it more regular, which is a bit of a shame because the silliness of language, I think, is important for thinking. It's a Monty Python piece, I suppose. But these are words that have become, the runs in red have become regularized, right? So, to be and to have, they're not regularized, but there are, many of these other words that have, whatever they had. There are lots of different past tenses that we've had over the years from different origins. There's the Norse invasion and then just stealing words and all sorts of things. But we don't introduce irregular verbs, right? To Google, we have chances, but no one does it. There's a real way of, there's a winning structure essentially for the past tense of verbs, for plurals as well, right? So, we have octopi, that's wrong because it's really a Greek word, so it should be octopodes, and octopuses is good. But kids will tend to sort of iron that out very, very slowly over hundreds of years. Of course, we still say children, right? Which is Anyway, so these things is a very interesting, kind of fun thing to look at. But there's a half-life for them, right? So 40,000 years would be when to have and to be might end up being completely regularized, and we have our code for communicating, at least in this aspect, will be clean and lifeless. Yes. I mean, it's not done by any central body. It's just people talking, and right, it's just a collective accidental thing that's happening. But it is. Well, there are rules that you see. Here are these patterns. Like, why can't it be here? The one that's on the bubble now in the last 10 years is wed, right? So two people were wed, but you can be wedded to an idea. I wasn't wedded to that idea. We do two things with that one, depending on its meaning. But they lose it. They run out of space. Okay, so that's a good place to stop. And I'll talk a little bit about technology, Moore's law and those things, and then we'll talk about power law size distribution on Thursday. Thank you. Okay.